All right, this is problem 1498. It's on page 642. A rotary power plow is used to remove snow from a level section of railroad track. The plow car is placed ahead of an engine which propels it at a constant speed of 15 miles per hour. The plow clears 180 tons of snow per minute, projecting it in the direction shown with a velocity of 40 feet per second relative to the plow car. Neglecting rolling friction, determine A, the magnitude of the force P exerted by the engine on the plow car, and B, the lateral force exerted on the plow car by the track. Okay, let's start off and look at this with a free body diagram so we can understand what's going on. Now, we just saw the video on the actual rotary plow in California. And so hopefully you understand what this is. If you're watching this video and you haven't been to the class, you may want to go and watch that video. It's a Discovery Channel video about 5 minutes long. So anyway, so you guys that have seen the video now recognize what I've just sketched here. It's the front face of that plow car. And if the snow is being shot off at an angle of 30 degrees with a velocity of, what did they say, 40 feet per second. And notice they said it's 40 feet per second relative to the plow car. So in other words, this velocity, since the plow car is moving, there's an absolute velocity component in the forward direction, right? So there's not just this. Okay, now it's moving forward at 15 miles per hour, which is about twice the speed that they said in the video. 15 miles an hour. Let's see. But think about it. If we're taking snow, we're bringing snow in that wasn't moving and accelerating it so that it now has a velocity in this direction, what direction of force do we have to apply to it? What do you think? It had no velocity, now it has some velocity. Here, let me give you a hint. Sum of forces equals mass flow VB less VA. I've essentially told you that with respect to ground, this is 0 because the snow is not moving with respect to ground, right? And this is a dot, not a vector. So what do you know about the direction of the velocity by comparison to the direction of the force?
Same direction.
Same direction, right? If we want to increase the velocity of the snow, which had no velocity, so it now has velocity in this direction, the net force must be in that direction. Now, with respect to ground, though, it also has a component in the forward direction, so there must also be a component of forward force, right? Because as we discussed, we're trying to accelerate the snow. It's sitting still, now it's moving forward at, well, in this case, 15 miles an hour. Okay? Now, we have to make a decision, though. Do we really want the incoming speed to be 0 or not? You see, with this equation, you've got a couple of options. You can either take the velocities with respect to ground or with respect to the moving item. In this case, the snowplow. What I'm going to do is choose to stand on the front of the snowplow, which would actually be a really bad idea in real life, right? If I fell, it would chew me up. So, but just for the sake of argument, let's pretend that we're standing on the top of the plow, watching snow come in at us and then be shot out perpendicular to our direction of motion, perpendicular to the tracks. Okay? So what we're going to do is write both of these velocities with respect to a coordinate frame that's sitting on the train. Okay? So I'll draw the Z direction. This is a right-handed coordinate system. I have no way to draw Z out from the board. If I had a three-dimensional board, I could do it, so you'll have to use your imagination with me and pretend that this Z is coming out of the board down the railroad tracks. Make sense? Now, as the train moves, this coordinate system moves along with it. Make sense? Okay. So we're supposed to find the magnitude of the force exerted by the engine on the plow car and the lateral force exerted on the plow car by the tracks. Well, if the plow car is not accelerating in this direction, then there must be some force from the tracks that's applying the horizontal component of this velocity. Just like there must be some force from the engine onto the plow car applying force to the snow in this direction, so the snow can be moving at 15 miles an hour. Make sense? Now notice the one thing they did not ask us for is the force from ground onto the plow car, because we'd have to include the weight of the plow car if we wanted to know that. But the force from the rails onto the plow car would actually be more than just the weight of the plow car, because it would also have to provide the force to accelerate the snow in the vertical direction. Okay. But they didn't ask for that, so we won't ask it ourselves. Let me call this force R, even though they didn't give us a name for that force. And essentially, this is just the force that the plow car will apply to the snow to get the x component of that velocity. Okay. Now, I can't draw a P literally coming out of the board, but I'll draw it in the same direction as Z, indicating it's supposed to come out of the board. And there's the force from the engine onto the plow car that causes the snow to accelerate. So now let's go and break up this equation. Now, before we move on, let me finish my discussion. You can take both of these velocities with respect to the plow car, or both of them with respect to the ground. Either way will work out, because all we're interested in is the relative velocity. And the relative velocity will be the same regardless of whether you take your frame on the car or on the ground. To show you that it works, I'm going to take it on the car. Okay? Now, let's see. Really, we have three equations. Sum of force in the x direction equals mass flow rate, velocity at the exit in the x direction, velocity at the entrance in the x direction. We also have some forces in the y direction. Mass flow rate, VBY less VAY, and some forces z direction. Mass flow rate, VBZ less VAZ. Which one of these equations do you think we are not going to use in this problem? There's actually one of these three we will not use. Which one? I think the Z is important. There's a force in the Z direction we need to find. So we'll probably use Z. Let's keep it in. Y. Y is the one we will not use. Why are we not going to use Y? Because they didn't ask us for the force in the Y direction, see? All we want is the force in the X direction and the force in the Z direction. Okay? So, while this equation is true, they didn't ask us for it, and so we're not going to use it. Okay, so now we've written both of the components that we're interested in. Now, what forces are we talking about? What force acts in the X direction in order to accelerate the snow?
The R force.
Good. So this is just R. What force acts in the Z direction to accelerate the snow? Just P. Now, as we discussed before, in the real snow plow, there's going to be a little more force P on it because of these wings that come out there. It's kind of like shoving a flat plate through the snow, which obviously would not be easy. Right? But we're just calculating the momentum part of it now. So here's what we need. We need the velocity at the exit in the X direction. That's right here. VBX. Notice this is VB. And we need VAX. What is VAX? VAX is the velocity in the X direction of the snow coming into the plow. In the X direction, the plow is moving this direction. What is the velocity of the snow sitting on the railroad tracks in the X direction? There is none. Right? This is 0. Right? Now, what about in the Z direction? Does the snow, if I'm standing on the plow, does the snow have any velocity in the Z direction? No, because remember we said that the snow is coming off perpendicular to the rail car, right? So as the rail car moves along, that snow also moves along. So the velocity at the exit of the snow in the Z direction is 0. Does the snow have any velocity in the Z direction coming into the plow? Yes, because think about it. If you were standing on top of the plow looking down, you would see snow coming in at you, right? So what speed is that? What is VAZ? 15 miles an hour, right? Is it positive or negative?
Negative.
It's negative, because notice our Z coordinate comes out this way. If you were standing on the plow looking at the snow would be coming in this way. That's a negative 15 miles an hour. So let's go ahead and convert. We may as well. We've got feet per second, so 15 miles per hour multiplied by, well, let's see, what are the conversion factors? Do you know?
I mean,
5280. Units are feet per mile, good.
1 hour per
1 hour.
600 seconds.
3,600 seconds. Be a little careful with this one. It's easy. This is a very easy one. You all probably know it by heart. But I've had students accidentally write 1 hour per 60 seconds. Of course, they meant an hour per 60 minutes, or 60 seconds per minute. So just be careful. Make sure you don't make that mistake of just not thinking. So hours go away, miles go away. We'll have feet per second. Please plug this in your calculator and tell me the speed. If you're watching the video, you should grab your calculator also and try it.
22 miles per hour.
22 miles an hour. Okay. You mean feet per second?
Yeah.
I probably said it backwards, or I heard it backwards or something. Anyway, so 22 feet per second. So VAZ is just negative 22 feet per second. Does everybody understand why it's negative? It's because we're looking at the snow, the kind of snow is coming in at us, which is opposite the Z direction, which goes out away from us. Okay? How about VBX? How would we calculate VBX? Any ideas? Cosine, that's right. So we want this component, it's touching the angle, so we'll have to take 40 feet per second times the cosine of 30 degrees. When you do that, what do you get? Using cosine of 30 a half? Or I'm not remembering it right. No, that's the .866, isn't it?
Yeah.
Okay.
It'll be 34.6.
34.6, thanks. So now we have VBX. Is it positive or negative or what?
It's positive.
Positive, because it's in the X direction. So VBX is 34.6 feet per second. So now we have all that we need, except we need the mass flow rate. What did they say the mass flow rate was?
180 tons per minute.
Okay, so let's work with that. Mass flow rate, 180 tons per minute. Now that's probably not the best unit, so let's convert tons to pounds mass. Do you know the conversion factor? 2,000, that's right. 2,000 pound mass per ton. And instead of minutes, we need seconds, so 1 minute is 60 seconds. Okay, so plug this also into your calculators, please. And let's see what we get. Should be 6,000, right?
Right.
So 6,000 pound mass per second. My goodness, 3 tons of snow every second. And that's reasonable. I certainly wouldn't want to be hit by this snow. Talk about a snowball fight. I'm bringing the rotary in. Just stand right there, okay? See you later. Okay, so 6,000 pounds mass per second. That's what goes in here. Same thing here. Why is it 6,000 pounds mass per second in both? Does that really seem fair? Shouldn't part of it be in one and part of it in the other? No. All 6,000 pounds every second gains 34.6 feet per second in the X direction. Okay?
I have a question.
Yeah, sure, please.
I'm pretty sure it's like that. So, like the VB and VA, what's the difference?
Difference. VB, anything with a B in it is going out from whatever it was that changed in momentum. A is coming in.
Okay.
So A is always entrance, B is always exit. Good question. Any others? Okay, well, I've got a question for you. When you multiply this out, what do you get? So for R is what, and P is what, numerically? Notice that both will be positive, right? There's a negative is positive. Grab your calculator, multiply it out, what do we have? And while you're calculating, let's discuss this a little bit. It doesn't really seem fair. I said we were going to start with, I started talking about fluids flowing. Snow's not really a fluid, right? It's a solid, but it does flow because you can chop it up and make it flow, like we're doing. So really all we're talking about is changing the mass of a lot of little bitty particles. So you can actually apply this to shooting sand out or flour or sugar or anything like that that's granulated. This would work just as well. Anyone have some numbers?
For R, I've got 207,600,
207,000,
207,600.
Oh. 07000,
600.
600. Okay, and the units would be pound mass feet per second squared, right? Pound mass feet per second squared. Are those units of force? Is a pound mass foot per second squared a unit of force?
Yeah.
Yes, it is. Is it a unit of force we're used to using? No. So let's multiply by 1 pound force per 32.2 pound mass feet per second squared. So that way the pound mass feet per second squared go away. We'll have our resultant, or our lateral force in units of pounds force. So now what do you get? So whoever had the 207,600, please divide by 32.2. What is it?
6,447.
It's a pretty good lateral force on the rails, isn't it? Over 3 tons. How about P?
We're at 4,099.
How much?
4,099 pounds.
Oh, 4,099 pounds force, thank you. So you went ahead and converted to pounds force, thank you, good. So basically, you wouldn't want to be between the plow and the engine, right? There's 2,000 pounds of force between those two. 2,100 pounds. Heck, I wouldn't want to be squeezed with 100 pounds. Okay. Now, here's another thing we can do. We can actually extend this problem because we just talked about power. In fact, it was the end of what, chapter 13, wasn't it, where we talked about power? Okay, so power is what? Power is force times velocity, right? So how much horsepower does the engine have to put out in order to push this rail car along? Okay, let's figure that out. Well, power is going to be, and let's use W dot from thermo, it's going to be the force P multiplied by the velocity. Now we've discovered the velocity, bless you, is 22 feet per second. So this is going to be, let's just round it up to 4,100 pounds force multiplied by the velocity, which is 22 feet per second. Now, of course, once you get this, and you got pounds force feet per second, divide it by 550, you'll have horsepower. Okay? So grab your calculators, don't put them away yet. 4,100 times 22 divided by 550 is how much? 164 horsepower. Okay. So you have to have at least 164 horsepower, which of course is small, right? That's not a major output. That's pretty easy to do, but that's continuous. Did you notice the power specification that they gave in the video for the rotary plow? 1,700, 1,900, about 2,000 horsepower. Now, is it possible to make a car engine produce that much? No. Could a car engine produce 1,000 horsepower or so? Possibly, maybe for a short period of time. But notice that an engine like this is designed to put out that kind of power continuously. Even a souped-up, racing car putting out 1,000 horsepower continuously is not going to happen. There's no way. You blow up the engine. Engines that are made to work like this, engines on a backhoe or any construction equipment, they may be rated at a wimpy 35 horsepower, but it's made to give that horsepower continuously, whereas a regular car engine can't do that. So there's significant differences in the design. Now that was interesting. Could we do the same thing with this? Because think about it. The reaction force required here multiplied by the velocity in the x direction should give us the amount of power required just for shooting the snow off in this direction. But if we wanted to, we could calculate the total reaction force. In fact, why don't we do that, right? We should just do it. Because notice, we don't necessarily have to break up the vector into two components. We could say the sum of forces equals mass flow rate times VB less VA. And it's pretty obvious that if I took a coordinate just in this direction, let me call this x prime, then this equation, I could write it simply in the x prime direction, right? And then the force that I would be solving for would just be however much force is required in this direction, let's just call it F, for lack of any original number or symbol. That's how much force is required to accelerate the snow at 40 feet per second. So let's run through that. So that force F would be the 6,000